So hello everyone, I'll now present my paper on an end-calling algorithm for the unsupervised word sense disambiguation. I'll explain my algorithm, the end-calling algorithm, and then compare it to other algorithms from the state of the art in order to see how it performs. So now first, I'll explain briefly what word sense disambiguation is. So as you can see, even in a very simple sentence like this, the villain ran along the bank. There is some ambiguity because, for example, here we don't know if it's bank, the building, or a river, for example. And you can see you have many possible senses. And to determine the right sense, actually, you have to determine which combination is the most likely in context. And so to do that, in fact, it's computationally very expensive. If you take a small paragraph, for example, if you evaluate all combinations, it could take you longer than the age of the universe to find a solution. So, of course, we want to have some methods to accelerate that and have answers as close as possible to human judgment while still doing it quickly. And so this problem is in fact central in natural language processing. So before going any further, I'll explain specifically the task I'm tackling. So here it's word sense disambiguation as a labeling task. So for a text, for each word, you have a sense inventory which says, okay, this word has that many senses and so on. For each word, you have to choose one of the senses and to assign the sense label to the word. So we're using an evaluation corpus from Seminole 2007. That's an evaluation workshop for WSD. And specifically task 7, which is a coarse grain task on all parts of speech and all words. So this is the most general word sense disambiguation task. And in fact, this campaign is a bit old. However, it's the latest one for this most general setting on the English language. Which is why we chose that. So now let me briefly introduce the outline of our presentation. So first, I'll present specifically the subdomain of WSD I'm working on, knowledge-based WSD. Then I'll briefly present the local measures we're using. So the local measures, in fact, are common to all these algorithms. And then I'll present the global algorithms that will use these measures to disambiguate the text in more detail. And then I'll move on to the evaluation and comparison of the algorithms, and then conclude and give some perspectives on future work. So first, let me briefly summarize what's being done in WSD. So there are three kinds of methods. Supervised methods, in simple terms, you have a large text where you already know the sense assignment, and then you use a classifier that you train to recognize each word in context by using this large text that it learns from. But the problem with that approach is that, well, you need a lot of training data, and you need humans to do that. So it's very expensive and very scarce. So really, these methods have very good results, but they're very expensive to set up, and they cannot scale very well on larger contexts, or if you change the language, it will be very expensive to retrain. Then there are unsupervised methods. They do not use any kind of assistance. They're fully automated. So for example, they'll use some corpus and look at word co-occurrence frequencies and then use that to disambiguate. But of course, the results are much lower with such approaches. And in fact, they're more appropriate if you don't have a sense inventory, which already tells you what are the possible senses. So this will be able to discover, in fact, the senses on its own. And then you have knowledge-based methods, which in fact exploit existing resources such as WordNet or other such lexical resources, which means, well, they're easy to adapt to other languages. You just change the result, the algorithm remains the same. As it exploits linguistic knowledge, well, it may be more accurate in terms of how humans perceive semantics. And, well, even though it requires resources, these kind of resources, they're the first resources available in languages. So sense inventories and machine-readable dictionaries. So they're really easy to implement in many contexts. So my work focuses on these approaches. And so now the local measures, they're in fact what constitutes this knowledge-based part. A local measure is in fact something that will tell me between two senses what's their proximity, how close are those senses. And so this measure will use the results to give a value that represents the closeness of senses. So here in a small example, this is called the last method. So it's a really simple method that has been proposed very long ago, but it's still a very effective method thanks to some recent extensions. So it's very simple. In fact, the original algorithm, for example, for a short noun phrase like pine cone, you consider all the possible senses, and then you calculate the similarity between all sense pairs. And the similarity here is calculated by the number of words in common between definitions. So, I mean, between this definition and this definition, for example, you can see an overlap of 2. You'll have a similarity of 2. And then between all the others, there are no words in common, so the similarity is 0. So, of course, on this very simple example, you know that this is the right solution given what you know about the context. So, the highest score in short. And now an extension of this algorithm that in fact makes it compete quite nicely with state-of-the-art methods, and that is the extended less similarity measure proposed by Pedersen and Banerjee in 2002. So they exploit in fact resources such as WordNet, which have a taxonomic structure. So here, for example, you have this thing, it's called the synset. It's just a series of words which represent the concept of a car. You have a small definition, and then you can see different links. So a hyperonym will be something, so the car is a kind of motor vehicle, that's a hyperonym. Then you have meronyms here, which are the parts of the car. You have many other relations. In fact, this is just a small example. And what you will do, instead of just considering the definitions of the two words, for example, car here and truck, so first sense of car, first sense of truck, you will also take the definitions of related senses. For example, for car, you'll take this text here, this definition, but you also concatenate all the other definitions. And thus you have an expanded context which will lead to higher similarity scores. So you'll be able to better distinguish between senses because there will be more contrast between them. So these similarity measures then will be exploited by global algorithms that from just these local measurements will be able to expand it to the scale of the text and tell you for the whole text what are the right senses. So in fact, this can be very simply explained as an optimization algorithm. What's the best combination with the highest value? So first, the encoding algorithm. So in fact, it's a heuristic based on the natural process of how ants work. So how they get food, how they bring it back, and in fact, how they can find the optimal path in nature. And so this algorithm is based on this idea. And here we've adapted it, in fact, to work for optimization problems rather than just search problems in the graph. So here I explain how it works in a short example. So this is the structure of the graph we use. So here you have one node for the sentence on the text, depends on the level you're on. Here we have a simple sentence which is mice pilot computers, and so we'll represent each word by a node. And then for each word there is a child which represents the possible senses. So these will be called regular nodes, and here we have nest nodes which will produce ants that correspond to each sense. So the property here of this graph is that you have first an energy value and then a vector. The energy value, well, is the resource the ants will collect, and the vector will in fact contain some semantic information about the neighborhood of the node, as I'll explain now. So let's take the example of an ant that's produced in this node here, mouse, as a device. So this ant, in fact, will pseudo-randomly explore this graph. Of course, here it doesn't have a choice, of course, it will go here, but the principle is that whenever the ant goes on a node, it takes one energy and carries it on with it, but also here you'll notice that it deposits some numbers. These numbers, in fact, they're numbers representing the words of the definition that corresponds to that sense. So whenever an ant passes, it will deposit some of the words of the definition. So when many ants pass, you'll have the sort of meta definition which will represent the semantic neighborhood of the node. And ants will use, in fact, this semantic information by calculating the overlap between their definition and that definition on the nodes to choose, in fact, the paths with the highest semantic score to find their way. So an ant will walk like this, explore the graph, accumulate energy. When it reaches a certain amount of energy, it says, okay, I have enough energy now, I'm going to bring it back home. Well, it's still pseudo-randomly will try to find its way back home. Of course, there is a high probability that it doesn't go back the same way. And for example, here I'll exhibit a very important behavior of this algorithm. It is if the ant wanders and reaches a sense that is not a sense of its own word, then by computing the similarity between this vector and the vector of its sense, it will be able, if the similarity is higher than a certain threshold, to build a bridge between this sense and its own sense. And when many ants build bridges, you'll have sort of interpretative paths in your sentence. And this constructive approach actually means we don't need to consider all combinations, but only those combinations which are most meaningful. So when ants run in the graph at the end, you can have a situation like this, with certain bridges that are more frequented by ants, so stronger. And that means the senses that are linked with, by those stronger bridges, they'll accumulate all the energy of the system, while other senses will starve. So what we notice is that the system converges on the senses that are most semantically relevant to the sentence, to this specific context. So now briefly I'll present the two other algorithms, so simulating annealing and the genetic algorithm. So these, they do not work on a graph, they work on a vector representation. So it's in fact a much simpler representation here. So let's say you start from a text like this, then for each word of the text you have one index in this vector, and the value in each index corresponds to a specific sense combination. For example, here you'll have the sense combination that corresponds with the first sense of the first word, then the second sense of the th word, and the fifth sense of the nth word, and so on. You'll have a vector representing one possible configuration, one possible combination. So the way these algorithms work, first simulating annealing. So first you choose a random combination, and then you will apply random changes to this configuration, and then using this local semantic similarity measure, you're going to calculate a score for the configuration by summing all the pairwise similarities. And by iterating the modifications, you can then make the difference between the scores between the modified configuration and the original configuration. If there is some improvement, you're going to take this new configuration as your current configuration. Otherwise, there will be still a probability of accepting inferior configurations, because in fact, when you're optimizing a function, you may in fact be going towards a local minimum or a local maximum, and you want to avoid that. So with this mechanism, you're able to explore other paths and avoid getting stuck in local minima. So in fact, this modification is repeated a certain number of iterations, and then after these iterations are passed, you're going to check if there has been a change. For example, you're making 20 iterations, going to check, okay, since this 20 iterations since the beginning, has there been any change? And if there has been no change, then you converge. Otherwise, you'll lower a parameter that's temperature here, lowering the probability of acceptance of inferior configurations. And that means as time goes on, at the beginning you're going to explore very broadly your search space, and as time progresses, you'll concentrate on a specific area so as to have the guarantee of convergence. And you're hoping that the final solution will be a good answer to the WSD problem. And then you have the genetic algorithm, similar principle, similar idea, but you have in fact several configurations at the start, random as well. And what you're going to do, you're going to calculate the score of all of them, sort them by the score, take the best individuals. For the best individuals, you're just going to swap, in fact, the selected senses, like reproduction in nature. That's why it's called genetic algorithm. These are like chromosomes. And for the rest, you're just going to clone them. So with that, you get a new population. From the new population, you just keep the best individual. And then, well, you just iterate that model. And you run this iteratively. At some point, you have some criteria saying, okay, now I'm stopping. There's no progression in the score, for example. It's stagnating. So, okay, I'm just going to consider the best individual now. I have my solution. Now, in terms of the evaluation, and before evaluating, there is a very important point. All these algorithms have many parameters, in fact, and it's useful to estimate them. So in fact, given some empirical evidence of how long it takes to run these algorithms, the encoding algorithm is much faster, so we're able to apply an automated parameter estimation method, because actually it takes about 90 seconds to run this algorithm, whereas the others, one of them is 25 minutes, the other one is 1 hour and 30. Actually, it's very difficult to do it automatically. For these, we made a manual estimation. So these are the parameters, and there's this other paper about the automated method that you can check for later. So now the results. These algorithms, in fact, they're probabilistic, so they may return different solutions every time. We make 100 executions, and then we just compare the average results. And, we use some significance measures to see if the differences are significant. So here on this first slide, they're very detailed results, but on this slide, I'll just point out here this column here, which represents the number of local score evaluations, so this last measure. And in fact, we're using this to try and explain why one algorithm is faster than the others. So you see here that in this first algorithm, the encoding algorithm, have only about 1.5 million evaluations. Simulated annealing, we have 4 million, and then here we have 137 million. And in fact, there is a positive correlation between the number of evaluations here and the runtime. So in fact, what explains the difference in speed is the fact that these algorithms will be more wasteful in terms of what they evaluate, and they'll make more wrong, they'll consider more wrong samples, whereas the encoding algorithm will be able to converge quickly while considering less wrong solutions. So now I'll detail the rest of the results on these graphs, as it will be easier to see. So in fact, as you can see, the encoding algorithm itself, due to this automated parameter estimation, actually reaches results about 2% higher than the two others. And on top of this, actually, this normal execution where we make 100 executions, we also apply the majority voting strategy. So for 10 executions, we consider all the solutions provided, and we count the most common one, and then we take that. So by doing this, in fact, the encoding algorithm has a huge boost in its scores compared to the others. And the others still increase by 1-something% when applying the vote. But the encoding algorithm, due to its quite high variability here, manages to reach a higher score. And in fact, we are able to reach this baseline here, which is the first sense baseline, which corresponds to the most common senses, that in a general context, in fact, it's quite good to just take the first sense. And then, by using these energy values on the nodes that I explained earlier, we're applying a weighted vote and manage to reach even better results, in fact. And as I'm going to show on the next slides, a comparison with other systems. So at the top here, we have the supervised systems where we provide huge amounts of examples. Here in bold, that's our algorithm, and then these are other algorithms that were present in that evaluation campaign. And as we can see, in fact, we're able to reach very closely the top supervised systems. And this is a very significant achievement, in fact, for a knowledge-based method, because we do not need any training examples or such, just a simple resource. So yes, in terms of the conclusions, the encoding algorithm is much faster. This enables us to estimate parameters automatically and then reach even better results. Because of this, it has very interesting perspectives. For example, we could find sets of parameters which work best for certain parts of speech. For example, just nouns, just verbs, and so on. And using voting strategies to combine those. And also, we're currently considering extending the system to a multilingual setting where we're able to disambiguate a certain number of languages automatically. They just provide a text in that language, and it will automatically tell you, okay, these are the senses for your text, whatever the language. Thank you for your attention. Do you have any questions?
Where you compare the other algorithms just after. it's a different method to compare the result if one. It's what you do, and in both phase, it is your method.
Well, in bold are the ones we evaluated in this paper, and the ones that are not in bold are systems that were evaluated on the same data set during the campaign in 2007. And in italic here you have other systems from the state of the art with more recent results. So these results here are from 2012 in fact.
Okay.
But the comparison is on the same data set.
Okay.
And as you can see here, the coverage is 100%. So in fact, these F1 values, they are the same from precision recall. So in fact, we're actually comparing them on exactly the same set of answers.
And we work in the same team?
Yes, we do.
And what is the difference? Because I don't see really I think there is a big difference, but I don't see.
Well, I mean, these are different approaches. I mean, we're both working on that distributional thesaurus problem. I mean, that's in fact a paper we discovered recently, which has very good results. So we're investigating their method to try and improve these results by adding these things from that other paper. Otherwise, I mean, my own topic will be more on multilingual lexical resources, how to use these algorithms to improve resources, and to use the improved resources to improve the algorithms. It's sort of that cycle.
Can I just ask you, in simulating annealing,
Yes.
you said that you introduce random changes.
Yes.
Is that, could you give me any idea about what these random changes might be? Or?
Well, for example, in one configuration you have one set of selected senses. So you say that this is the sense combination I'm considering. So you say random change, okay, random number on the vector side. So you take, for example, the 10th word, and you say, okay, the sense selected was 1, and now I'm making a random change, so now it will be 3, for example. And then you're just going to evaluate this change. How good is it? Did it improve something? So it's generally the sampling method.
Testing the
Yes,
system.
exactly. Yeah.
More questions? People are probably quite tired actually now. We've been listening intently now for the last 3 hours. So I don't think I have any more questions like that. Comments? Just a few comments quickly. Did you enjoy it? Or one question I will ask you, was it difficult to follow because Amber was speaking quite quickly? Or did the visual support provide sufficient support?
It's too quickly, but very clearly. The support is good, so it's easy to follow.
Okay, so you understood me. The other is you
I think it's what we have to.
I think Alan has given you a very, very good example. That's not to say that the other presentations have not been good, but it's true that Alan has a high level of English, and well, we feel that you're at ease speaking.
And I have to mention as well that I did this presentation last week in India, so in fact, I'm very well prepared.
So the training is important. And how did they receive your presentation?
Also, it was quite good. I mean, I didn't get many questions. People understand more or less the method, but yes, the presentation went quite well and smoothly.
And so, are you working in collaboration with teams in India, or is this just a congress?
Well, it's an international conference. Actually, one of the top conferences in the field, which was in India. Actually, our team, we have some collaboration with the team in IIT Mumbai. We had some interns from there and so on. I mean, I'm not directly myself collaborating with them, but we do have some collaborations with that team.
Very interesting. Well, thank you, Angela. And I think, yes, I mean, your mastery of English is good, and your problem, Mark, so I think the slides supported your